Warm welcome to all the participants. um, we'll start by looking at what this technology called oneAPI is. And then eventually I'll introduce you to the actual programming that's needed to make this work, and then how easy the whole scheme of things is. Okay, so oneAPI is an industry initiative. It's a technology initiative by Intel. The idea here is the industry as a whole is facing this difficulty. And so Intel has come up with a solution that can be adopted as and how people see value. And then Intel has come forth to produce or provide solutions with the initiative that it has come through. So the initiative itself is referred to as the oneAPI, and then the Intel tools associated with it are referred to as the Intel oneAPI tools. So in today's world, if you look at HPC, either HPC or AI workloads, the workload itself has varied degrees of representation in memory. So the workloads are represented in memory in different forms. And according to the way in which it has been represented, certain hardware becomes more efficient, or certain hardware has evolved to be more efficient to work with such representations. So say, for example, if you look at the CPU is efficient in working with many different kinds of data structures, many different kinds of data types housed in different data structures. Say, for example, you have a structure in which struct or a class in which you have various things like a employee database or a student database, the name, the age, the grade, date of join. So each field is a different variant, meaning different type of variable. So it's a heterogeneous mix of different variables, different types of variables, and the CPU becomes very efficient, or it has evolved to be efficient in working with all these different forms. On the other hand, if you look at representations for speech or for images, speeches, and vector in memory, which is nothing but a single dimensional array. Or if you look at an image, it is multiple sheets of two-dimensional arrays in memory. So in both of these cases, the GPU finds itself extremely useful working with them. And then if you have your own representation from a software perspective, and eventually you brought it onto an FPGA by creating a RTL for it and a bit stream, etc., then that's your own representation, and you have your hardware working efficiently with it. Whatever the case may be, and then there are other accelerators. Say, for example, you have the tensor accelerator, you have neural network accelerators, etc. In all these different cases, every one of these devices require you to learn a different programming language, or at least work with different sets of tools, right? So in some cases, the programming language may be the same, but then the tool set needed to make this happen for you might be very different. So all in all, when you have these data-centric workloads and the data-centric hardware requirement, and pretty much most solutions today require multiple hardware usage. You may not be able to complete your solution just by adding more and more cores and running more threads on them. So you may end up using different kinds of hardwares. And in this scenario, now you have to have a team which has multiple skill sets, and then the code change becomes very difficult. Say, for example, you were running a fast Fourier transform on the CPU and you've made it all good and efficient. Now you transition to wanting to run it on the GPU. It may not be as efficient as it can be. You may have to retweak it, even if you got the compiler compiling the same code per se. So that's the paradigm we are in. So that's the situation most of us face every day in our industry, in our institution, etc. So the idea is, how do we solve this problem? Is there one way to program all of these different devices? Or can we have one single point of entry and then use these different devices as and how we choose them dynamically in the program? So that's where oneAPI comes in. So this initiative by Intel kind of sits on top of the hardware layer, and then it helps you with a single point of entry. So you write one code and then you offload portions of this code onto different pieces of hardware. And then you can programmatically change it as well. There is quite a bit of ways in which you can programmatically choose a GPU, CPU, CPU of a certain kind, GPU of a certain kind, FPGA, etc., to offload the GPU. Now you can dynamically say, look, I am going to try the eigen on the GPU and see how efficient things are, so on and so forth. So that's basically the whole idea of this initiative. It's a single point of entry to various hardware offloads. So single point of entry from a programming perspective, from an efficiency perspective, and from a tool set perspective. So all the three kind of make your life much easier and makes it to be efficient. So the two main parts of this initiative are referred to as the direct programming interface and the API-based programming interface. Direct programming interface basically refers to this language, which is referred to, which is called data parallel C++. The new nomenclature is SYCL, SYCL. So it is called SYCL. The language itself is called SYCL, or sometimes it's referred to as C++ SYCL. In the traditional sense, it is referred to as data parallel C++. So that's one aspect of it. So you write your program in SYCL. And then the second aspect of it is these API-based programming libraries. So the libraries give you a footprint for the different hardwares that they support. So thereby, by using these library components, you are efficient, or you are more compatible with the hardware by construction. So that's the whole idea here. So two aspects, the programming language and then the API based, these libraries that you use within your program to make your code efficient. Okay, so the programming language called SYCL is based on standard C++. So it uses all the syntax, semantics, and the constructs of C++. On top of that, there are these Keronis SYCL constructs. The SYCL constructs basically help you offload portions of your program to various hardware. So that's where that fits in. And then the entire syntax is pretty much C++. All the different attributes and all the different features of C++, modern C++, is available to you as part of this programming language. And then there's a third portion, which is referred to as the community extensions. So community extensions are aspects of the programming language that are developed by Intel and supported by Intel in their compiler to enable quick transition of legacy C or C++ programs to DP++ or SYCL. So that's where the community extension comes. At this point, okay, I forgot to mention, this is a standards language. So the standards are published and anybody can build compiler for this language. Now, the community extensions are not part of the standard, but the rest of the language is standard. And the hope is over time, these community extensions also become part of the language definition. Okay, so the libraries play a very, very important role. So it not only makes your code modular, reusable, all those useful nature of the code, but when you use libraries come in handy as well. But each of these library components have their own footprint for the CPU, for GPU, and for FPGA, as the case may be. All of them may not be available for all these different hardwares, but wherever they are, they are. So when you have a different footprint, the library has already fine-tuned that specific functionality for that particular hardware. So thereby you get an efficient implementation for the underlying hardware, which means to say your program now, because of the use of these libraries, have become efficient by construction. So just in layman terms, say for example, you had a Fourier transform. You had built it for the CPU, you transition it to the GPU, so you are losing some efficiency. You want to refine tune it in terms of working on the GPU. Instead of that, if you were using one of these library components, they had a CPU footprint, they had a GPU footprint, and the associated one gets used. So thereby your program doesn't need to be fine-tuned in that aspect at least. Okay, so there's a whole ecosystem that's been developing, that's been gradually grown over time. And so the whole idea here is nobody should be apprehensive in picking up this language. So the quick question that arises is, what about hardware that are not Intel centric? So in that case, what happens? As I mentioned earlier, it is a industry initiative. So it is up to the industry if they find the value in it, so they can adopt and they can support the language. So what you see in the world today is you are able to run DPC++ or SYCL on NVIDIA GPUs. And for that, there's a software called CodePlay, and I think CodePlay is acquired into Intel right now. So you use this software and then you will be able to run DPC++ program on NVIDIA GPUs, and similarly other hardwares as well. Okay, so now we spoke about the initiative and kind of the fundamentals in terms of what this initiative brings to the table and how the industry, either you as a programmer or you as a producer of different hardware, can take advantage of it. Now, let us look at what are the tools, what Intel offers as part of the oneAPI toolset. So this slide kind of shows you four units here. One is referred to as the compatibility tool. Then there are multiple language supports as part of the oneAPI offering that Intel does. Then there are libraries. And then there are analysis and debug tools. So this is basically what Intel's offering is as part of the oneAPI tools. So the compatibility tool is a source-to-source converter. So it converts CUDA source code into SYCL source code. At this point in time, the observation or the statistics is 90 to 95% of the code typically gets automatically converted. And areas or portions that are not converted will be left with inline comments. So you can look at these comments and then accordingly adopt your program in the new language. Okay, so as far as the tools are concerned, Intel has tools as part of its oneAPI offering in the design space, debug space, and the fine-tuning space of your software development or different phases of your software development. In the design phase, there's a tool called Intel Advisor. And in the debug phase, you can use the Intel distribution of GDB. And for the fine tuning of your application, basically tracing your application, understanding where its drawbacks are, etc., you use this tool called Intel vTune Profiler. It does give you hints as to where you can improve the performance. But then there are other areas where you understand how your program is functioning. And then eventually you can slightly re-architect the program to make it more efficient. Okay, so all the offerings of Intel in the oneAPI space are distributed as toolkits. There are different toolkits. So there's a base toolkit, which is like a common denominator. So you first get the base toolkit. And depending upon your area of interest, you can get any one of these different or more than one domain-specific toolkits. So the domains that are addressed are HPC, IoT, rendering, AI analytics, and OpenVINO. OpenVINO is also kind of related to the AI analytics system because it's a different tool. It's been packaged separately. So HPC, IoT, rendering, analytics. So that's basically the different toolkits catering to, and then you have the base toolkit. So there's another easy way for you to adopt oneAPI, and that is referred to as the Intel Dev Cloud. So Intel provides a free development cloud wherein you can get an account by signing up with your email ID. I think the time duration is for 60 to 90 days and it is renewable. So in the Dev Cloud, there are different kinds of hardware populated, and then all the different aspects of oneAPI software is available to you. Apart from that, you also have a lot of starter code. So there are different programs that you can run. You can run it through this Jupyter notebook. So thereby you can see the steps, you can get the output result, so on and so forth, just to kind of get you started. And after that, you can upload your own code or you can build your own code there and try different hardware, different libraries, different aspects of oneAPI. Okay, so this is a slide in case you already have been using Parallel Studio or System Studio. So this is the equivalent for a Parallel Studio customer. The base toolkit, HPC toolkit is the equivalent. And in the System Studio case, it's the base toolkit plus the IoT toolkit. Okay, so with pretty much any of its new releases, Intel produces a lot of benchmarking results. So for each of these toolkit under known existing frameworks, known existing prominent softwares, these benchmarks are created and pretty much all the benchmark results are available on the Intel website. You will see I'll give you a little more information on the benchmark when we get to the different toolkits. Okay, so this is all your resource links. So software.intel.com, oneAPI or oneAPI.io. There are community forums, there are regular trainings, there are webinars. Intel even has a YouTube channel now. So you can kind of get connected on all of these and then build up your repertoire with oneAPI. So in summary, for all the different diverse workloads that we are looking at, especially in a heterogeneous compute environment where you have to use more than one kind of hardware, it becomes apparent that you will spend a lot of time in learning new languages, learning new toolkits, etc., to make your program efficient. So this problem, the solution that Intel is offering as an initiative is referred to as oneAPI. And as part of its own oneAPI offering, it has, before that, I should also summarize saying the offering itself consists of a language that helps you work with various different hardware, one point of entry, and a tool set basically catering to that language. And then eventually a set of libraries that you can use for one is for reusability and second for easy migration from one hardware to another. So that's part of the initiative. Then as part of the Intel offering, you have the base toolkit, the compilers, the libraries, and then the analysis tools. The base toolkit and then the different domain specific toolkits, which houses all this. Okay, so I'll spend the next 5-10 minutes on the different toolkits, a little more detail. So the base toolkit. So every toolkit contents can be analyzed in these three verticals: the direct programming interface, the API-based programming libraries, then the analysis and debug tools. So as part of the direct programming interface, there's multiple language support in the base toolkit. The primary one is the DPC++ compiler, then the DPC++ compatibility tool, Intel's distribution of Python. And then there's another piece of software referred to as the FPGA add-on for oneAPI based toolkit. Then there's a whole slew of libraries, all the way from standard template library, libraries to building threads, libraries for neural network construction from basics, then libraries for building your analytics application, then libraries for some video processing, etc. So there's a whole slew of libraries. I have a few slides on the libraries as well, so we'll come to that. Then as far as the analysis and debug tools, you have the vTune profiler, you have the Intel advisor, and the Intel distribution of GDB. So again, the design phase, the debug phase, and then the fine-tuning phase of your software development. Okay, so the DPC++ compiler is an LLVM based compiler. So it has a runtime environment, and basically this sits on top of your hardware layer, and it basically helps you switch or offload portions of your code to any of these different hardware. So that's basically what the compiler construction looks like, and it is backward compatible with C++. You can compile pure C++ code with oneAPI, with this DPC++ compiler. Okay, compatibility tool, we saw this is a source to source conversion, CUDA to SYCL. Okay, so we'll look at few of the libraries. The first one is referred to as the DPC++ library. And this is standard template library. So standard template library adopted to DPC++. It also has parallelism built in, and it also has the boost functionality. So, and when you are using the compatibility tool in the migration process, some aspects of this library also get used. Then the deep neural network library, this is called the DNN. So oneDNN, that's what the nomenclature is. This is a library of primitives. So if you're building your own neural network framework, you can use this library to make it more efficient and even faster. And the footprint is available for both the CPU and GPU. So that's something you may want to note in each of these slides. The footprints are available for both these different hardware, which means to say it will give you an efficient construction, efficient run on both this kind of hardware. Okay, so the video processing library, as the name itself suggests, is for videos, and you have encoders, decoders, scaling, and a few other functions that are available. And once again, the footprint is for both CPU and GPU. Collective communications library is for distributed learning. So if you're doing distributed learning of your neural network, you might be using some framework for it, like Horowitz, etc. So the whole idea is it's on a cluster. There are different nodes, and the nodes are connected using some kind of a backplane connect. It could be OmniPath, InfiniBand, Ethernet, whatever the fabric that you have. And on top of that, you are running MPI, and this library is a layer on top of that. So that's basically how distributed learning works, and Intel has a library for it, and this is called CCL, oneCCL. Okay, so those were just few slides on the library. Then there are others like MKL, IPP, thread building block, etc. So those for the other operations. I mean, the slides are just kind of giving you a feel for them. Okay, so let's look at some of the tools. One of the primary tools is the vTune profiler. So when you run your application on a hardware, you basically you have, assuming you have an understanding of the different blocks of the hardware, architectural blocks of the hardware, while you write your program, you do a certain things to take advantage of the branch predictor to make sure things are cache contained, etc., etc. So then you run your program to find out which portions of your program. I mean, the simple analysis is to quickly find out which portions of your program are taking a lot of time. Is this some kind of an SIMD block? Can I parallelize it? So you go on and see if you can vectorize some of these areas. If vectorization has not been done automatically, then you'll try to figure out why it has not happened. Then you go ahead and fix your code to make it happen, so on and so forth. Those are the low-hanging fruits. Now, if you come a little further, you're looking at, you thought you are completely cache contained, but because of some kind of virtual sharing or some other mechanism, you're not completely cache contained. So these are aspects that you will know when you look at vTune profiler's logs. So here it will tell you whether it's a compute bound problem or whether it's a memory bound problem. Then what kind of cache misses are you seeing in terms of the total cache access itself? What is it that you could have gotten, why you did not? So that's when you start looking at your code code, and then slightly re-architecting some portions of it so that you get better efficiency. And so for all this to happen, you need a very powerful tool which looks at the performance monitoring registers inside the chip and then builds the necessary outlook for you. So that's what vTune Profile Address. It's a very, very powerful tool, and it's available for quite variety of languages like C, C++, Fortran, Python, Java, etc. And it's also capable of analyzing it for CPU, GPU, and the FPGAs as well. Of course, it does work with DPC++ or SYCL code. Okay, so the other tool is the Intel Advisor. This is more at a design level. So the idea here is you have implemented your code, you want to understand some of the design aspects or change them or get a feel for it so that you can improve it. So one of the very simple ideas is, what about vectorization? There are so many SIMD blocks, which is nothing but data parallel for loops. So you have initiated vectorization, auto vectorization compiler option 2, but then certain portions haven't gotten vectorized. So you want to find out. So you have something called the vectorization advisor, which tells you which loops are vectorized, which are not, what can be done to make them vectorized, so on and so forth. Now, the next thing to do is, next level of parallelism is threading advisor. So it can advise you in terms of where you can add threads and what number of threads will give you what advantage in terms of performance. So that's the next level. Then there are other analysis it does. There is an offload advisor. So offloading is when you come to language SYCL. So here the whole intent is to offload portions of your code to different hardware and see what is the efficiency, and then have some kind of a statistical knowledge as to how much time the entire program took to execute. So that's basically the offload advisor. Now, again, in a DPC++ or a SYCL program, different portions of your program are running on different hardware, which means all of these are concurrent, meaning they are running in parallel. When things are running in parallel, there's a strong need for making sure synchronization is happening. So for example, you don't want the host code to keep continuing while you need the results from the accelerator code, right? So you have to put down some kind of a synchronization barrier at that point in time. Now, how do you analyze such a program? So you analyze such a program using what are called as the flow graphs. And Intel Advisor can build a flow graph for a SYCL program and then kind of show you where the kernels are executing and what are their synchronization points. The last one is a little more complex. It's called the roofline analysis. So for a CPU plus memory system, for that kind of a system, there is a maximum efficiency that can be achieved for a given instruction. So for example, again, let's go back to, you're adding two arrays. So it's an integer addition. It's an SIMD block, two arrays of the same size, assuming it's aligned in memory, etc. So you're adding them. So these are integer additions. So for integer additions, given your CPU and the memory combination, there is a maximum efficiency possible. And that is referred to as the roofline. So in the graph below, and this relates to different memories. So the roofline is first plotted for the hardware that you have. And then your point of operation below the roofline is plotted. So for example, the red dot on the slide is that point of operation. The whole intent here is to understand why the red dot is where it is, and then try to see how you can move the red dot upwards towards the roofline so that you're operating more closer to the maximum efficiency possible. And that's basically what roofline analysis is. Okay, and given all the complexity with respect to the hardwares, the different threads, vectorization, etc., you need quite a powerful debugger to kind of show you all the different details and help you work through it. And that's where the Intel distribution of GDB comes. So it helps you debug these complex environments. Okay, so the last piece of software is referred to as the oneAPI for FPGA. This is part of the base toolkit. So when you take a SYCL program and when you want to convert it into an FPGA bit stream, there's a lot of steps that are involved. So this code, if you are doing it on your own, you will write RTL, then you will simulate, make sure that RTL is good. Then you will synthesize the RTL and hopefully it will fit into that FPGA. And then eventually you will make bit streams of that RTL, of that particular synthesis, and then load it into the FPGA. And then you'll have to build the interface around it and then start working with it by writing your own uh, code to connect to it, etc. So that's the process, and usually it's a long process. Now, this software, oneAPI for FPGA, automates that flow. So underlying it calls the synthesizer and eventually builds a bit stream out of it and loads it into the FPGA. So if you're working with FPGAs, you will need this software. Okay, so that was about the base toolkit. Then look at the different domain-specific toolkits. The first one is the HPC toolkit. So as far as the HPC toolkit is concerned, HPC is predominantly Fortran and C++, Fortran C and C++. So the classic compilers are included. So the way to read this slide is the dark blue ones are part of this toolkit. The lighter blue ones are coming to you from the base toolkit. So the two classic compilers are included here. And then to build your Intel MPI programs, to scale your program across the cluster, you have the MPI library here. This is the Intel MPI library. And then as far as the tool sets are concerned, three tools are added. One is the Intel Inspector, Intel Trace Analyzer and Collector, and then the Intel Cluster Checker. The Inspector is correctness tool for memory and threads. The ITAC is for tracing your MPI program, compute, transport changes. Then the Intel Cluster Checker is a housekeeping tool for the cluster itself. Okay, so the benchmarking. So in terms of benchmarking, the whole idea is to show you that the current technology is equivalent or superior to what is out there. So if you take, for example, an application like GROMACS, it's typically built in C++, and then now it is built in DPC++, and people were using accelerators with CUDA. Now CUDA code has been converted to DPC++ using compatibility tool. And then we are running this DPC++ program that got converted using code play back on the NVIDIA GPU. So that's kind of the setup. And then the entire program is run in this fashion and compared with the current technology to kind of see where we stand as opposed to how much of evolution has happened. So that's basically what these benchmarks do for you. And most of this result is available, published on the Intel website. Okay, the AI analytics toolkit is predominantly for folks who are working in building AI ML applications. So here you have the Intel optimization for TensorFlow, PyTorch, neural compressor. And then in the machine learning domain, there's scikit-learn and XGBoost. Then for data analytics, there's Intel distribution of Modin and OmniSci. So for Python users, NumPy, SciPy, those libraries optimized for Intel are available. Apart from all this, there's something that's referred to as the model zoo, which is pre-trained neural networks optimized for inferences on the GPU and the CPU, where you can quickly build applications on top of it. So these are benchmarking results with respect to this specific toolkit. Rendering toolkit, I'm not an expert in the rendering domain. This is not my domain, but some of these standard libraries are available for inferencing, for working with efficiently on the CPU and the GPU. And some benchmarking with rendering. Then the IoT toolkit, predominantly here you will find the C++ classic compiler. Then there's an IoT connection tools library, and then the inspector, which is the correctness checker, and some benchmark with it, and quickly run through distribution of OpenVINO. So OpenVINO has a model optimizer through which you can put your trained neural network. It comes out with intermediate files, which is an XML and a bin. Those are referenced through the inference engine. And this is how you kind of enhance the performance of your inferencing. So these are the different toolkits that are available to you from Intel. And that's about the Intel's offering in the oneAPI space. I will go over a little bit of the DPC++ program to give you a feel for what it looks like. Okay, so this is the paradigm we are working with, and DPC++ fits in as part of the oneAPI initiative. And it is nothing but the C++ and some SYCL constructs. Okay, so let's look at a DPC++ program. So what you see here is it's a very simple hello world program, basically adding numbers and then printing out the outcome. This is all, this example is available on DevCloud as well. So early on, we have instantiated a buffer of integer in a certain range. Then we submit this parallel for in this queue. And then you also please note that the buffer.getAccess is a call that is made. So three aspects in this program that needs attention is the queue, the buffer, and the parallel for. The buffer is how you kind of control synchronization. Then the queue is how you offload code onto a different hardware. Then finally, the parallel for is how you run your kernel or your workload. The way you compile your program is dpc++ minus f, that's SYCL unnamed lambda, whatever your source file is, and the output. Okay, so DevCloud once more. So now let us look at the details of this. So this is the lambda definition of the kernel. So there are multiple ways in which you can define your kernel. The examples in my slide are all lambdas function. And then there are, you can do it using functor objects. You can also do it using interops. Now kernels are submitted to the queue using either parallel for, single task, or parallel for work groups. So parallel for is your classic openMP for with a parallel construct. Then single task is for task parallel, and then parallel for work group is when you create work groups. I have another slide for it. So the piece of code that runs on an accelerator that is offloaded is referred to as a kernel. That is code that is executed on a specific accelerator. Now, as you saw in the previous slide, one second, I'll go back to the slide. As you saw in this previous slide, the portion shown with the green bracket is running on the host. The portion shown with the yellow area is running on the device, and then there is host code again, right? So you don't want the second host code to run till the accelerator has completely finished its work, even though these pieces are now running in parallel, right? So that's where the get access construct comes in. So the get access basically creates a synchronization barrier. So you've come back, the host is waiting for the accelerator result to be available before it can continue its execution. So there is a concept of work groups, as we saw. So you create a work item. So from the work item, you build up hierarchy to make a work group, and then eventually you can create an ND range out of it as well. So the work item itself can be mapped onto the constructs of the CPU, and then eventually you build the hierarchy so that you have your single instruction, multiple data kind of a model to execute your entire workload. Okay, so another concept to notice, as I said, buffers, queues, and the parallel for are the three important things to note here. We will see the buffer. As far as the queue is concerned, the queue is what points to a hardware. So multiple queues can point to a given hardware, but not the vice versa. And then within the queue construct, you have various way of selecting whichever hardware that you're looking for. So if you're just looking for a GPU, you can do a GPU selector. On the other hand, if you're looking for a GPU with a specific part number, that can also be mentioned. And this way, if it is available, it will go on and execute with respect to that queue. Okay, so the kernels in parallel and the data flow diagram. So that's basically where we are right now. So this is the data flow diagram. So as you can see, there are two buffers here, A and B, and then there are 4 different kernels. Now it is necessary for you that kernel A executes on A first, then it is followed by kernel 2. Kernel 3 can execute on B, but kernel 4 needs both A and B, and then A and B have to be finished with kernel 1, 2, and 3 respectively. And that's basically what is shown in the data flow diagram on the right. So in order to achieve that kind of a synchronization, we use the get access method. So a dot get access, it's like a semaphore. So it's basically takes control of that particular buffer A, and then you do whatever the activity. It could be on buffer A or it could be something else. This is the way you maintain synchronization between these different kernels. Please note again, all these kernels can execute in parallel if you let them be. Okay, so this is called the buffer accessor model. You instantiate these buffers and then you call these accessors to be sure that this kind of a synchronization happens, works for you. Okay, so in general, the execution is asynchronous. There's nothing to say when what is executing. They are all devices executing in parallel. So you have to explicitly do the synchronization to get control of your execution path. Okay, so the same point emphasized again. Okay, so there are other aspects of SYCL DPC++ as part of the extension. So one is one very important aspect is the unified shared memory. So we'll look at this. So memory can be allocated on the device or it can be allocated on the host. So you can follow what is referred to as the explicit transport or it is implicit. So automatically data can be accessible and explicit data movement is also supported. So implicit or explicit. Now, if you have existing code which are using pointers, then you can use what is referred to as malloc shared, and then implicit data movement happens within the system. You don't have to worry about it. So data can be allocated on the device or on the host depending upon your code. So wherever you are in the code and depending on where it is allocated, it happens as, and then if they need to be migrated, you have to explicitly do it, or you have to use malloc shared kind of construct to implicitly make it happen. Okay, so USM is a mechanism, especially when you are migrating code. You can still, I'll show it here. So you can still continue to use the buffers and then use the buffer accessor along with your regular malloc instead of malloc share and get the same result. So here you have declared your arrays, you have initializing it, and for each one of them, you're keeping a mirror buffer, and then you're using these get access constructs to kind of hold on to synchronization. You do what you do in your kernel, and then you get to the next block, right? If you're using USM, the same code changes like this. You're using shared malloc share. This is your USM array. Then this is the pointers that you were referring to. You can use the q.wait to make sure this queue has finished this submission before it gets to anything else. Okay, so there are different ways in doing the synchronization. Synchronization is an important aspect which you have to handle in your program. So you get an event back when you submit. Now you can use that event to create a dependency for the next submission, or you can use that event and wait on that event as well. So this is the whole idea of subgroups and work group, etc. It's a hierarchical way of building your SIMD blocks. That's basically what it is. And I don't want to get into too much of detail on it because I'm kind of running short of time. So just give you a feel for it. Okay, so queues are out of order by construction. So if you want to make them in order, then you will have to instantiate in order queues. Else you have to use these kind of depends on weight, etc. So if you just successively submit, the jobs on the queue can be out of order. Okay. So data flow pipes is basically the flow diagram that I was talking to. So the transition between the host buffer and then the host and the devices in terms of programmatic way in which you can transition data, or it automatically happens implicitly. Okay, so when we saw this minus f SYCL unnamed lambda is needed because for every lambda's function, there's a need to name it. So the compiler has used this compiler directive to, compiler option to override that. Okay, so that's a little bit about DPC++. I think now we will take some questions. Is the code supposed to be lock-free? Can you kind of elaborate a little more on that?
Yeah, I think this was asked when you were showing parallel for on the screen. And I guess it is about the body being lock-free, perhaps?
No, the body.
The
so as I said, the queues on their own are out of order. So if you submit, you don't know which submission happens first. And then if you have A, B, and C, you have to explicitly do the synchronization among yourself. There is nothing else that you can, I mean, there's nothing within the code that happens. It all has to, you have to take care of synchronization completely explicitly.
And this is synchronization of the jobs you are saying, or synchronization of the data being accessed?
No. Synchronization of the jobs through the buffer construct. You have offloaded different portions of your code to different entities, meaning different pieces of hardware. Now, all of these hardware are executing in parallel. So it's up to you to make sure, okay, hardware 1 has finished this job before I can get hardware 2 to do something. Or you could submit 2-3 jobs to the same queue, meaning to the same hardware, right? So for example, if you have a GPU of 3000 cores, then there's nothing, and you're only using few hundred cores per job, you can submit all the 3 in parallel. But unfortunately, if there is a need for synchronization among them, then you'll have to use it either using the event and do a wait on it, or you have to do a in order queue, things like that.
Thank you. Oh, okay, just one question just popped up. Which method of allocation has overhead malloc or malloc share?
Okay, so it depends on case by case basis. I have seen both possibilities. So in certain cases, malloc with buffer itself works very fine. And malloc share just makes your life easy in terms of readability. It doesn't change a whole lot. And then the synchronization. So you will have to kind of play around with it, and also depends upon how much of movement you have between the device and the host in terms of these data.
Ooh, we have more questions. You have time? Shall I go next?
Okay. Yeah. I think we have 7 minutes more.
Okay. How much is the cost of cross hardware synchronization? When is it better to just compute on one?
So the whole idea here is you were not able to get your job done on one in the time you want it to be. Right? So for example, if you're doing real-time video analytics, so sometimes in a big frame, and depending upon what you're doing, it can take more than 200 milliseconds for a frame to process. then how do you process more than 5 or 6 frames in a second so that you get the efficiency you want? Then you have to use an accelerator. You don't have a choice, isn't it? So that is the condition under which, see, if you are okay, if it's a non-real time, non-time critical application, okay, I can get it today. It's okay if I get it tomorrow. Then you don't have to use an accelerator at all, right? Save your money, add more cores.
Yeah. Okay, next one is, if I queue 3 or 4 SIMD tasks at once, are they running in parallel internally?
If you, yes, they will run in parallel, provided you haven't put a in order queue. The queues are out of order by default. So if they can run in parallel, there is some kind of a load balancer on top of it. Yes, it will run in parallel.
Would it run on a separate core also, like multiple cores are doing theirs in these, perhaps?
Yes, yes. The whole
Course,
idea
right?
of a queue is mapped to a different piece of hardware. Yep. Sorry about
Right.
that.
The next one is, I would imagine that creating the kernels and the pipeline itself is an art form. Any suggestions on some reference material?
There's a good book which is referred to as the data parallel.
You'll have to hold it at your chest or
Oh,
something like this. Yeah.
okay.
Yeah, perfect.
So this is a good reference book. I can type it up in the chat as well. Yeah.
Yeah, please.
It's,
Thanks.
yeah, it's more of engineering than artwork.
Oh, really? You want to correct him? Okay. Niket Sharma asks, for architecture exploration analysis, if CPU, GPU, or FPGA is modeling using system C TLM or TLM, how one API methodology can be useful? Or is it limited to actual hardware only and not the virtual hardware?
Yes, that is correct. The second half of the question is correct. Yes, it is when you have already written the program, the modeling can be done in terms of vtunes, analysis, etc. It is not at the preconceived stage where you are running it through TLMs, etc.
Most of the GPUs are black boxes. Any resources on the insides of a GPU?
Can't think of one right away, but I'm sure there are.
If you use oneAPI, do we need to do that? Just
You
asking.
will see whichever you may need to do it again. So you bought your GPU and you thought it will give you so much of a performance gain, but it did not. Then you'll have to know a little more about it, go through its traces to make sure your program runs as fast as you want it to, or you thought it should.
Makes sense.
So
Measure.
a black box remains a black box. You have to make it gray one day or the other.
Right. Thank you, Sam, for that question.
Any further questions?
Good, I guess.
Cool.
Any
So I
last
think
ones? Yeah, you were saying something by the time somebody.
no, I mean, if there are, I think we have a few more minutes, maybe 3 or 4. For the
One more.
Go ahead.
Thank you, we want that. Yeah, so they're going to type. So good. Thank you for the information. So you mentioned, just I'll use up the time for my question. You said there are 75 algorithms that you have implemented with
75. Did I say that number somewhere? In what
uh,
context?
the STD algorithms are implemented in oneAPI.
Oh, that slide. Yes. So standard template library has been there for almost 30 years, even before I started working. So it's evolved over years. And then what you get in that DPC++ library is the standard template library with boost and the parallelism built in. The threading is built in. I mean, I don't know exactly the 75, the slide said 75, 75.
Yeah. Okay. There's a question. As per the example shown, parallel jobs can be run. If yes, it's developer's responsibility to put into a queue in order to achieve parallelism.
So when you thought through the program, you have figured out which portions of the program can run in parallel. So that's the first requirement. So all programs cannot be run in parallel. There's a law for it. So the portions of the program that can be parallelized. So these days you were parallelizing it using, say, threads or vectorization. Now you have the option of offloading it to another program through this program itself without having to look at it as a different device, call a library, call some interface code, etc., etc. So that's basically what is happening here. And this whole thing has been abstracted to you in the form of a queue. A different device is now available to you in the form of a queue. And then you just, as if you're submitting it to the queue, you submit the parallel for, and then it runs on the device. So that's the mechanism that has been adopted to make this happen.
Thank you. I see there's a short question in the chat. Is it C++20 compatible?
Yes, it is. It's C++ standard 15.3 or something like that. Yeah. 20, I have to check, but I know it was 15 something.
Okay, you got to check because C++ standards would be either 11, 14, 17 or 20.
I forgot. I mean, I don't
Yeah,
remember the
yeah.
exact number. So yes,
Yeah.
there are new releases of DPC++ standards every now and then. So,
Okay, you're talking about the DPC++ standard.
and then the compiler also. I think Intel makes a release once a quarter. So there are updates once a quarter. So you know it through the compiler, isn't it? What gets supported.
Good. That looks like the last points to discuss. I guess we are almost out of time also. So at this point, I think, I don't know, any final thoughts you wanted to say?
Thank you,
I-
everyone.
Okay.
So try it out. So just get on DevCloud and try it out. It's fun.